Now let's go to the second part of the comparison test with the limit comparison test. So the limit comparison test says that you have two sequences of positive terms, and the limit when it goes to infinity of the ratio of the sequence is going to be a positive number c. Then it depends on what the situation is. If both series are going to be either convergent or both series are going to be either divergent. So if you have that one of them you already know is convergent, then the other one is going to be convergent as well. If you're picking one that you already know is divergent, then you're going to know that the other one is going to be divergent as well. And for this number c, it got to be a positive real number. But we can also have a variation of this when the limit is 0. So if you have that the limit when n goes to infinity of an over bn is 0, and you have the information that the series of bn is convergent, then the series of an is also going to be convergent. So now to test on that, let's actually go and see some examples of this. So let's go here to the board. So the first one is one type of series that we already know a little bit what happens with it. Let's see this series of an as 1 over 2 to the n minus 1. We already proved by comparison that this was convergent, but let's use again this one that is a convergent series that we know to figure out what happened with that. So this is an, and I'm going to call this one bn. So we're going to take the limit when n goes to infinity of 1 over 2n minus 1 over 1 over 2n. And so to simplify this, we get limit when n goes to infinity of 2 to the n over 2 to the n minus 1. But because we're trying to calculate this limit and this is infinity over infinity, then the most easiest way that I can do anything here is just divide everything by 2n. So this is really limit when n goes to infinity of 1 over 1 minus 1 over 2 to the n. So I divided everything by 2 to the n, and it's giving me this. Now notice that when n goes to infinity, this goes to 0. And so this whole limit is going to be 1. So my conclusion, and this is something that you got to write exactly in this way, is that by limit comparison test, then since this converges, then this one is going to be convergent as well. And that's it. This is the main use of the limit comparison test. I have one series that I want to know if it's convergent or not, and I have another one that I already know is convergent. I make a limit between the two, a ratio between the two sequences. I get the limit. If the limit is a number bigger than 0, then I can make conclusions with regard to convergency. So now let's go to another example. Now let's go with the different series. Consider the series n equals 1 to infinity of n over n squared minus cosine square of n. So in this series, if you take a look at this, this term is not very relevant. Cosine square of n is bounded by 1. So this is really a series where the dominant terms is this n squared down here. And because we have this n squared here in the top we have an n, we cannot see it over here like n over n squared. So I'm prone to compare it with the series 1 over n. Now the series 1 over n diverges by integral test. We saw that in last video. So we're going to use that to compare with this particular series. We're going to have to be very careful when we're doing the limit. So here we're going to get this situation where we get limit when n goes to infinity of n squared over n squared minus cosine square of n. But really, if we divide by n squared, then this limit is transformed into an entire different limit. This is transformed into knowing what is the value of the limit when n goes to infinity of cosine squared over 1 over n squared. And so what happens is that cosine squared is actually bounded between 0 and 1. And so we can divide by n squared. And so we're going to have that cosine square of n over n squared is bounded between 0 and 1 over n squared. But when n goes to infinity, that's going to mean that the extremes are going to go to 0, and then the limit when n goes to infinity, when n goes to infinity here of cosine squared over n squared is going to go to 0. And so if that goes to 0, this means that this limit goes to 1. And because it goes to 1 and the series below diverges, then the series is going to be divergent. So by limit comparison theorem, the series of n over n squared minus cosine squared of n diverges. And we got to write all this just to showcase that that's our argument. Now let's go to the next one. In the following series, we have the dominant term really is this exponential to the minus n. Sure, below we have that n and cosine square of n are included. But if you see this here, this e to the minus n is really like it's below. So because it is e to the minus n, you can see there's like 1 over e to the n. And so it's like e to the n is below. And so really, we can just consider this as 1 over e to the n, compare with that. And because this is a geometric series with r equals 1 over e less than 1, this is convergent. So our idea is that likely this is going to be a convergent series if we compare it with this. So if we go and calculate a limit, this is limit when n goes to infinity of e to the minus n over n plus cosine square of n over e to the minus n. And I'm going to put this like 1 over 1, so I can use e to the minus n. This is going to be a limit when n goes to infinity of 1 over n plus cosine square of n. And so now we have a different limit again that we're transitioning to. And this limit is the one that's going to decide what happens. But now to get this limit, because cosine squared oscillates between 0 and 1, I can go ahead and establish that inequality. And then I'm going to add n to everything. So I'm going to have that cosine n plus cosine square of n is between n and n plus 1. And because I have that, then I'm going to be able to use the squeeze theorem again. Notice that 1 over n plus 1 is less than 1 over n plus cosine square of n. I'm just flipping this with this with this, and gets me this one. Now if I flip this with this and this with this, I'm going to get that 1 over n plus cosine square is less than 1 over n. And when n goes to infinity, that means that this piece goes to 0, this piece goes to 0, and that implies that this limit is going to go to 0. So we are now on the second case of the limit comparison test. Fortunately, because this series is convergent, then this series is going to be convergent. So by limit comparison test, I have that e to the minus n over n plus cosine square of n is convergent. And notice that that's one of the reasons why I'm always dividing below. Is because in the case that is 0, is if it's convergent, then immediately it's going to give me the convergency of the series above. If it's different from 0, if it's 1 or if any other number, then whatever. Because if this is convergent or divergent, then the other one is just going to be convergent or divergent. But in the case that is 0, it's only going to matter if the one below is convergent. So that's why I often use to divide by the other sequence below. Now, another example will be the sequence here from n equals, the series from n equals 2 to infinity of n minus 1 over n to the 6 plus 1. So again, kind of what I do here is compare with something. I'm going to ignore this plus 1 and I'm going to think that this is a square root of n to the 6. So this is like n to the 3. And with an n here, n over n to the 3 is like n squared. So I'm going to be comparing this with n squared. 1 over n squared. So this is a convergent series by the integral test. You can prove that using the integral test. So I'm going to do limit when n goes to infinity of n minus 1 over square root of n plus 6 over 1 over n squared. And so this transforms into the limit when n goes to infinity of this is n cubed minus n squared over n to the 6 square root of n to the 6 plus 1. And again, this is an infinite over infinite scenario. And so I'm going to now divide by n cubed up and down. Why by n cubed up and down? Because if I divide by n cubed up and down, I'm going to get 1 minus 1 over n here. And over here below, n cubed can be seen as a square root of n to the 6. So I can just write this as 1 plus 1 over n to the 6 by dividing n cubed up and down. And so notice that when I take limit when n goes to infinity, this goes to 0, this goes to 0, and this whole limit is going to 1. So that tells me that by limit comparison test, again, this series of n minus 1 over square root of n plus 6 from n equals 2 to infinity converges. Now, last but not least, we have this 7 over n plus 1, n times n plus 1. And you can probably think that this converges, since this has been proven before that by partial fraction, this is a telescopic series. But notice that I can also compare it with n squared, since this is going to be the n times n plus 1 is n squared plus n, so the denominator term is n squared. And then if I make limit comparison test, this is 7 over this over 1 over n squared. So this in terms of the limit will be 7n squared over n squared plus n. And I don't want to do anything complicated here. So just as a reminder, you can actually use L'Hopital's rule here. This is an infinity over infinity situation. So you can think of this as the limit when it goes to infinity of 14n over 2n plus 1. And this is again infinity over infinity. So you can go limit when n goes to infinity of the next, which is 14 over 2. And that's just 7. So this whole limit is going to be 7. And because it's bigger than 0, so by limit comparison test again, we have that this series from 2 to infinity of 7 over n plus 1 converges. Okay? And so that's some examples of limit comparison test. Now, the next thing is that we have used both the limit comparison test and the comparison test to show that a series converges in comparison to another series. But what happened with that is that we might be able to estimate a sum of the series by comparing the remainders of the other series. So for example, if we have that the remainder of my initial series is just the numbers after n plus 1, up to infinity, then by the comparison of the series with the second series Bn, I can do exactly the same. I can check the remainders, and let me call it, this is a Tn. There's a typo here, but essentially I'm checking what is the sum of the remainders of the second series B. And so what happens is that since An is less than Bn, then I'm going to have that Rn, so the remainders for A are less than Tn, which is the remainders for B. And so if I have something like Bn is going to be a P series, I can estimate the remainder by doing the integration. And so on and so forth. If it's a geometric, then I can do the same calculation. So, for example, we can use the sum of the first 100 terms to approximate the sum of the series 1 over n cubed plus 1 and estimate the error involved in the approximation. So, just let me pull a little bit of board here. Well, it seems I cannot simplify this more. So series of 1 over n cubed plus 1. And I want this from n equals 1 to infinity. And so first 100 terms. And I want also to estimate the error. So to do that, the first thing that I'm going to do, of course, is to make the calculation of this by the comparison test. So clearly I can compare, now probably you're not surprised, with 1 over n cubed, since n cubed plus 1 is bigger than n cubed. So that means that 1 over n cubed plus 1 is less than 1 over n cubed. And so because of that, I can use the comparison test as 1 over n cubed converges, then 1 over n cubed plus 1 converges. And now in terms of the estimation, notice that I can say that Tn, which is going to be the comparison for this, gotta be less than the series from, let's say, n to infinity of 1 over x cubed, right? And so we did this before. This is essentially 1 over 2n squared. And so this is saying, well, notice that this is the remainders of 1 over n cubed that are going to be bigger than the remainders of 1 over n cubed plus 1. So when I have that relationship, and I'm just considering, well, let's use n equals 100. So I can have that r of 100 is going to be less than 1 over 2, 100 squared. And if I approximate this with the calculator or computer, this is going to be 0.005. So it's a very small remainder. Now, I can also, of course, compute what's going to be the sum from n equals to infinity by approximating this with the first 100 terms. And this with the first 100 terms, which I calculate with a computer because will take forever. This is like 0.68645. And you're going to know that this has an error of less than that. So the sum is actually pretty good approximation of this error is a very good approximation of this sum and the real result that I'm going to have. So that's the end of the comparison test and the estimations that we can do in terms of the error and other values.